Okay, I think we're ready to start. So it's a great pleasure for this afternoon seminar to welcome Professor Siddhârta Mishra. Siddhârta is a professor at ETH Zurich. He's quite famous in particular for his work on numerical schemes for conservation laws, hyperbolic equations. He has received many distinctions. And today he will talk about a topic which has been lately of interest to him, named application of deep learning to partial differential equation. So Sid, without any further wait, we are listening to you.
First of all, thank you very much, Albert, for the introduction, as well as to you and other organizers for the invitation to speak here. It's really an honor to speak at the Laboratoire Jacques-Louis. So I took the liberty of slightly changing the title of my talk. The content is still the same, but the title is a little more succinct. Okay, so let's proceed. Some people say that we are living in an era of machine intelligence, and it's sort of justified because today machine learning, artificial intelligence, permeates so many fields of our life, right? Whether it's machine translation, facial recognition, more recently protein folding, and in many, many sectors of human activity. And sort of the central players in the success of machine learning are deep neural networks, mathematical objects called deep neural networks. I'll talk about them in some detail. But another central feature is the availability of big data. And by big data, I mean that we are talking about tens of thousands to hundreds of thousands to millions of training samples. And please remember that in mind, that this is a big ingredient to the success of machine learning. Now, the question that I'm going to ask at least is, can deep learning impact scientific computing? In particular, the computations of PDEs, partial differential equations. And I don't have to say this in this audience, PD subatomic scale all the way to the universal scales and everything in between. And we can't find explicit solutions except in the simplest of cases. So we have to resort to numerical methods. My screen is, no, it's working fine. And numerical methods, traditional numerical methods like find differences, find volumes, find elements. Many of you in the audience have made pioneering contributions to these things. They are highly successful, right? We know that very well. Even in my research group, everything from the computation of supernovas to clouds to tsunamis to flows around rockets, all this has been done with traditional numerical methods. But it's fair to say in this day and age, we are somehow hitting the limitations, many limitations. But the one that I will focus on or encapsulate my discussion today will be about high dimensional PDEs. And this was in the original title, if you remember. Now, high dimensional PDEs can arise in two different guises. The first one, of course, is if the physical dimension itself, space, is high dimensional, as it happens in Boltzmann equation or in different versions of Schrodinger's equation in PDEs, then the dimensionality is somehow explicit. On the other hand, there are other problems where the dimensionality, the high dimensionality, is much more implicit. And this is what happens in the case of parametric PDEs, a topic that many of you, including Albert, has studied in some detail. So let me give you my sort of notation about parametric PDEs. So this is the notation. So D is a spatiotemporal differential operator. U is the solution of the parametric PDE. It depends on space and time. And it also depends on parameters. These parameters, they're finite dimensional, but could be very high dimensional. And where do these parameters come from? They can come from uncertainty quantification, random PDEs, where we are interested not just in studying single realizations of the PDE, but in statistics like mean and variance and so on. In this context, these parameters, they parameterize the probability space in some sense. Another sector, another field from which these parametric PDEs can come from is optimal control, design, and so on, where these parameters take the role of design variables. So for instance, this is an airfoil, and these parameters parameterize the shape of the airfoil. So again, this could be 20, 50 dimensional. This computation is done with a 40-dimensional parameter space. So these are examples of parametric PDEs. And there are many, many other places where these examples can show up. Now, what's the issue? The issue is that okay, give me 1 second. Yeah, the issue is that these parametric PDEs, their computation leads to what are called many query problems. What is the meaning of that? So remember, we are interested in the solution field, the spatiotemporal solution field as a function of the parameters. in many cases, observables like lift and drag in the aerodynamic problem as a function of the parameters. And what we need in the design process or in uncertainty quantification is many hundreds, thousands, tens of thousands of realizations of these parameters. That's why you get these kind of many query problems. And of course, the obvious issue is the high computational cost. And how expensive is this? So remember that, okay, here's an example. So this is a computation of a compressible flow, Euler equations, compressible Euler equations in 3D, very big computation, 10 billion degrees of freedom. And we have developed over 5-10 years of optimized code for this, I would say. And a single simulation at 1000 cube takes about 300 node hours on a top range supercomputer, the best one that we can access to in Switzerland. However, single simulation is not interesting in this. What we're interested in statistics, in mean, variance, and so on. And that requires 500 to 1000, and even that is under resolved. Let's say if even 500 simulations, and if you put a cost on it, it is roughly 7,000 Swiss francs or 7,000 US dollars, even with my ETH discount. We don't have to pay it because it's paid by the project, but that's the cost that we are looking at. So just imagine if you look at more realistic problems, how expensive these kind of mini query problems are. So we need to do something. We need to lower the computational cost. And one way to do so would be to approximate the solution fields or these observables, which are functions of these parameters, high dimensional parameters, with deep neural networks. So this is the first time that deep neural networks make an appearance in my talk. So these days, everyone is aware of networks. I know that Bruno is teaching a course on them. So everyone is aware, students are also aware. So just for notation, I just write down what they are. So these are mathematical objects. These are functions. They map finite dimensional, possibly very high dimensional, but finite dimensional input into a very high dimensional, possibly finite dimensional output. So just a function. But this function in turn, is a function of compositions. So it consists of compositions, multiple compositions. So these are compositions, and each element of this composition is consisting of very simple functions. Affine, what is called a weight matrix multiplied by your input plus a bias vector. And this is in turn acted upon by a very simple scalar nonlinearity. What are called scalar activation functions. This could be rectified linear units, hyperbolic tangent, and so on. So remember, affine nonlinearity, affine nonlinearity, affine nonlinearity, and we keep on repeating this. So this is the sort of the structure of the object. And the point is we are going to approximate a target function. Here, capital L is in my target function with these objects. And how are we going to do that? The reason we can do that is we have some tuning parameters. So these weights and these biases, these are the tuning parameters. I can tune them or select them to match my target function or to approximate my target function. And to do so, the usual process is that I choose a random set of points in the parameter domain. This could be a high dimensional space, but I choose a random set of points. You have to give me the data. So these are sort of labeled values at these points. And then I try to adjust the parameters so that this mismatch, there are various loss functions that are possible. This mismatch is as small as possible. And to do so, we use a stochastic gradient descent algorithm. There are different variants that are available. So the algorithm itself is rather simple. You just have data, you fit the parameters using stochastic gradient descent. But the question is, can this work? Can we approximate solutions of PDEs, observables of solutions of PDEs by this method, right? And the answer is in principle, yes, because I think all of you know this, that these objects, these compositions, these deep neural networks, even shallow neural networks, are universal approximators. How universal? As long as I'm given a measurable function, which maps a finite dimensional space to a finite dimensional space, maybe we can take a compact set for simplicity, then we can prove that, or an open set for bounded set for simplicity, then we can prove that indeed this is universal. You can make it as small as possible, the error as small as possible. Of course, it's not very informative because you also need some quantification. How many neurons do I need? Layers do I need? What is the structure or the distribution of weights? Then you need to do something quantitative. This is also available these days by many people. I think some credit should go to Yarotsky, who really did it at some depth some years back. So the point was, if your function is Sobolev regular, so if it has S derivatives, if it's in this Sobolev space, then roughly speaking, the size of the neural network, the total size of the neural network scales like this. So if it has a ReLU activation function, then you need deep neural networks. The number of layers is given logarithmically in the error. But if you have other activation functions, for instance, if you have the hyperbolic tangent, then 2 hidden layers are enough. So you don't need deep, but you need wide neural networks. So the size gets reflected here. And this seems like good news unless until you start investigating or examining the estimate. So it depends on two things: scaling. It depends on the regularity. More regular a function, easier it is in principle to learn, but which is good. On the other hand, it also depends very badly, exponentially, on the dimensionality. The smaller the dimension, easier to learn. But this is exponential now. So if you are even in 6 dimensions, this can become a very, very large number. And essentially, this says that if we look at this estimate, we can learn nothing practically, in principle. Of course, in practice, this could be different, but in principle, because they're hit by the curse of dimensionality. So the first step would be to sort of enable the application of these techniques in PDEs, is to alleviate, is to overcome this curse of dimensionality. Thankfully, these are a series of mathematical results proved by many, many different people, including my colleague Christoph Schwab. We have done some work in hyperbolic PDEs, but for different kinds of PDEs: elliptic PDEs, semilinear parabolic PDEs, nonlinear hyperbolic PDEs. You can actually show that this approximation error, this best approximation, scales polynomially in dimension. And not just polynomially, these polynomials can be small. Like for elliptic PDEs, these are very small. Even for hyperbolic PDEs, these are like 1 or 2. So the message here is that indeed, in principle, PDEs are more structure, solutions to PDEs are more structure. So we can indeed approximate them by neural networks, by relatively small neural networks. But that's not the end of the story, because remember that this is just the best approximation result. In practice, we have to find these neural networks, right? So the total error, at least an estimate on it, is given in terms of this famous error decomposition. This is the part that I've already spoken about, the best approximation result. But you also have what is called optimization error. I'll talk about it at the very end of my lecture. But for the time being, let's say that what we can do is we can a posteriori compute it, because this comes from the so-called training error. So in practice, we know what it is. But the last bit is what is called the generalization error in machine learning, which is, remember that we are always trying to approximate. Okay, here, let me write. So this is an integral here. It's a norm. It's an integral. And we are going to approximate it at random points in this case, approximation sort of. So by a quadrature. So this is going to lead to some error. This is what is called the generalization error. And there are different techniques in statistical learning theory, because these things are correlated. So you can't just use central limit theorem. So one technique, for instance, uses concentration inequalities and so on. And ultimately you get, skipping the details, there are many. Skipping the details, what you get is the rate that you want, which is square root of n. Remember, that's Monte Carlo, but there is some logarithmic correction. So this is not so bad till you start. So the bottom line is, what I have done through these arguments is that my total error scales in terms of the neural network, the hypothesis space that I'm talking about, and 1 over square root of the number of training samples. Even if this guy was small, let's say, even if it's order of 1, still we are in trouble. Why is that? Because remember that this is 1 over square root of n. So roughly speaking, to get 1% error, 10 to the power minus 2, I need 10,000 samples. And this is where, to me, the crux of the problem lies, right? Remember that even a single sample took me a big supercomputer 100 node hours. 10,000 samples is going to lead me to absolutely nothing. So this is somehow the essential problem that I want to convey, that in scientific computing, we don't have access in general to big data. This is different from like face recognition or playing a video game or playing Go or something like that. You have lots of data there. Here, at best, I would say we have moderate amounts of data. So we have to really learn in a data poor regime. We have to work with, let's say, 100 to 1,000 samples. That is sort of I would say, the maximum number that one of in general. Of course, there are special cases where this can be done. So how can we train and learn with a few samples, or relatively few samples, than what is done usually in machine learning? Of course, we need some tricks. Numerical analysis gives us some tricks. At least I'll mention a couple of these tricks. The first trick is, why should we stick to random points? Remember that my data is generated by numerical simulations. So I can design where I take that data from. So one idea would be to use low discrepancy sequences. Elementary numerical analysis, we use them, for instance, in quasi-Monte Carlo integration and so on. And the idea is that these are equidistributed. So this is just a unit square. And I look at random points, and these are blue dots. And you can see in many of these little squares, you don't have a single blue dot. So random points have a high discrepancy. On the other hand, Sobol points, Halton points, and so on, these are specifically designed to be equidistributed. So most of these unit squares have these points. And if you have a little bit of regularity, bounded variation essentially, then one can prove an error estimate like this, where your total error, or the generalization error, scales like 1 over n, of course, with a logarithmic correction. But 1 over n is much better than 1 over square root of n, because 100 samples is much better than 10,000 samples, right? So this really makes a difference. And if you have more structure, like elliptic and parabolic PDEs, I refer back to some famous results obtained by Albert in this direction. We know that the mappings are holomorphic. We can exploit that, and this we do with Chris Schwab. We use something called specially designed extrapolated lattice points, and then you can even get rid of the curse of the logarithmic dependence in dimension, and you have even a quadratic scaling. So this is, for instance, with a 16-dimensional elliptic equation, 32-dimensional elliptic equation, we have quadratic in the number of samples. So with few samples, we can really learn this problem, which is very good. And there are other tricks, but let me give you a little more realistic results. So here's a problem that I really like, because you can do something about it. So this is a flow past an airfoil, an inviscid flow past an airfoil. And you have an airfoil which is parameterized by 20 parameters here, the shape of the airfoil. And this is just done with a code that I developed in my group, and it takes about 40 minutes. It's a very high resolution computation. And what I want to do is to predict the flow field when I change the shape. This is the essential idea. So now I ought to predict the drag or the lift or other quantities of interest. So I take 128 training samples. So I spend the time, train this with fairly small networks. The largest networks that we need here have 10,000 parameters. And the point is that 40 minutes, and this is prediction based on the neural networks that we have trained. And the error is about 1.7% for the whole field. It can be much less for the lift. It's of the same order for the drag. And then you can see the point here is that it took 40 minutes to do it from a numerical method, but to predict it using a neural network for the whole field took me 1/5 of a second. So you have really 4 or 5 orders of magnitude gain. And if you're just interested in one number, which is the lift and the drag, you can get even more orders of magnitude speed up. And here the choice of these low discrepancy sequences was essential because I used 128 training samples. If I didn't, then it would take much more points. Here's another example done using the same technique. You want to predict tsunamis in the Mediterranean. Believe me, they can happen. And there's a lot of interest in studying them. So there's an earthquake near Crete, and then the tsunami waves are generated. We want to study the time series at different points in the Italian coast. And again, the state-of-the-art simulation, this is done with people in Malaga and people in Italy. This takes about 60 minutes, the state-of-the-art simulation. But if you do it with neural networks, there's a big parameter, 11 parameter parametric domain, it takes less than a second. And you see that this is the worst result that we got in this particular setting. This is somewhere Calabria, and the time series is still fairly accurately computed. So you can do fairly realistic problems with these techniques. The other technique, maybe I very quickly mention, is what is called active learning. So this is very useful in PDE constraint optimization. People working in PDE constraint optimization in Paris. And the idea is that, again, you want to approximate, you want to use the neural networks as a surrogate, right? You want to replace the PDE here, or the numerical solution of the PDE, with the neural network. Now, of course, you can just like I showed you, just train and then just do it, right? It's very cheap, so it should work. However, there is a problem. If you remember that my optimizers could very well lie along a manifold curve in this particular case. And if I train based on random points or Sobol points in the whole domain, unless until I have a lot of points able to sort of learn this manifold or learn the properties of the solution around this manifold well. So this is not a good idea. So what we came up with is an algorithm which is iterative, it's active. So you don't fix the training points a priori, but you adapt them to the data. The details are not that important, but the idea is that you take initial screen of points, train your neural network, run it through a surrogate, do the optimization, and use the sort of pseudo optimizers as training points, and keep on iterating. So there is some sort of geometric convergence, at least in the convex case. And the end result is, by doing this adaptivity of training points, you can, for instance, this is a classic optimization problem. You reduce the drag by 50%. So these are the, let's say, optimized shapes. And the point is, you could have done it with a classical method. It means this is not at all the claim that it gives you a new optimizer. You could have easily done it with a classical method, but it would have taken you more evaluations. It would have taken you about 2,000 evaluations of the PDE solver. Here, with approximately 50, 60, 70 evaluations, you get the same result. So you get an order of 20, 30 speed up fair speed of order of 20 and 30. And as you can imagine, this kind of adaptivity helps a lot with Bayesian inversion. So we have a project in that, and it really, this active learning is a key ingredient in that. So the bottom line is, in this setting, if you learn how to deal with small amounts of data or moderate amounts of data, there are many problems that can be solved. However, let me start with the first caveat in this. It seems too smooth otherwise, right? Here is the first caveat. The first caveat here is, or second caveat, because the first one that was that we don't have access to big data, is that this approach that I told you, supervised learning, it required full knowledge of the PDEs, right? Because I was using some numerical simulation in order to generate the data. But more importantly, I needed access to a parameterization, because everything was parameter to solution to response. Now, these parameterizations, for instance, the tsunami parameterization has been developed over 50 years. The parameterization here has been also 30, 40 years long. So these problems people have studied a lot, and there are good parameterizations available. But if you want to study something new, or if you want to study PDEs that arise from social dynamics or whatever, then you may not have access to these sort of bespoke parameterizations. Then how do you do? Because everything relied on this parameterization, right? Now, when there is no parameterization, of course, you can do it empirically. If you have a measure, you take a lot of samples from that measure, and then you can parameterize it. This is done, for instance, in statistics with the PCA algorithms. But again, if you don't have that kind of data, what do you do, right? And this is where operator learning makes an appearance. It's a very new topic. It has been around, maybe I would say, for the last 1-2 years. And the idea is to do some non-parametric PDE solutions. So far it has been always parametric. We want to do it like in non-parametric statistics. We want to do it non-parametric. And where does the operator come from? Remember, in any PDE, what we have are some solution operators at the back end, right? So for instance, you take the initial data for a time-dependent PDE, or the coefficient of the forcing term for a stationary PDE. And then all that we do is we extract the PDE solution at the final time, or the solution in the whole domain. And this operator is a mapping between a Banach space in general to another Banach space. Okay, so infinite dimensional mapping. And what we are going to do is we are going to learn this entire mapping, the whole solution operator, rather than parameterizing and then trying to learn the parameter to output map. So we just learn the whole solution. And we learn it with deep neural networks. But of course, plain vanilla deep neural networks are not going to work, right? These are finite dimensional mappings. Now, what you want to learn is an infinite dimensional mapping, an operator. And this is where operator learning comes in. There are many, many different frameworks that are available. But let me just very briefly mention one, which is what is called deep nets, or deep operator nets. Now, these come from the 1990s, from the work of Chen and Chen. But more recently, George Kanedakis, he has somehow picked this up, and he has made it sort of deep. These were shallow networks before, and there are a lot of impressive numerical experiments that he has. But what I'll try to explain to you is sort of my take on why these things work, right? So first of all, remember that we are going to approximate an operator, which means that my input is a function, my output is a function. So I have X is a Banach space, Y is a Banach space. What is done here is, let's start with the output end, right? So let's start with the output end. Remember, my output is a function. So probably the easiest thing would be to approximate it as a span of some basis functions. Okay, so it's a function. So I approximated some span of some basis functions. These basis functions could be Sobolev regular, could be continuous functions, Holder continuous functions. We know that neural networks are universal approximators. So we can just as well replace them with neural networks. So my output of this operator would be spanned by a set of neural networks. And these neural networks, in the parlance here, are called trunk nets. Okay, so remember that. So I have a set of neural networks which span my output space. This is where this affine span comes in. But the coefficients of this span of these basis functions, these have to come out from somewhere. So they have to come from the input, right? Remember, my input is infinite dimensional, a function. I can't operate with infinite dimensional objects, so I have to project them down to finite dimensions. So this projection is sometimes called encoding in this terminology. And for instance, you can just choose a bunch of random points in your domain, and you can just take point-wise evaluations if you have sufficient regularity. If not, you can take local averages, linear functionals. So this is what is called encoding. So you take an infinite dimensional object and project it down to finite dimensions. That's the thing here. And remember, at the back end, I have this lifting, which goes from a finite dimension back to infinite dimension through this span, right? So all that is left is, from this finite dimensional object, I want to read out the coefficients of my span. And so I have a finite dimensional input, a finite dimensional output. Any function here, measurable function, can be approximated by a neural network. So all that I'm doing through this architecture, it looks a bit complicated at first, is that I have these three components. First, project down using an encoding step. Then I do an approximation. These are the coefficients in this. And finally, I lift it up to infinite dimensions using these trunk nets. So the coefficients, these neural networks are called branch nets. The spanning neural networks are called trunk nets. So the architecture itself at the end is enough sort of these objects, and the whole thing is called a depot net. So instead of having a single deep neural network, as we had before, we have now 2p plus 1. P is the number here, 2p plus 1 deep neural networks, but these are all trained simultaneously. So when we do the training, these are weights and biases, free parameters. We determine these free parameters by training them together, and these are done simultaneously. So they are trained at the same time. And as I said, they are very successful in numerical experiments. But can they work? Can they really approximate operators? And the answer, which is contained in this very lengthy paper, and I can only give you a sample here, is yes, in some sense, because what we can do is, again, just like we did for deep neural networks, not we, but this was done by Cybenko and so on, many, many years ago, one can prove a universal approximation theorem. So remember, we had for deep neural networks can approximate any measurable function. Here, of course, infinite dimensions, so you have to fix a measure, assume that there is a probability measure on L2 or some Sobolev space, and then you have a measurable operator mapping one Sobolev space to another. Then for any arbitrary accuracy, I have a depot net which will approximate it. So you have essentially the same approximation, universal approximation theorem, modulo the fact that for each measure, this depot net is going to change, right? Because it is different measures. This is the price that one has to pay. But of course, this is not quantitative. To go quantitatively, you have to really dig into the details of this operator. Remember, I'm going to approximate this guy here, this operator, by this encoding, by this approximation, and by this lifting, this reconstruction. And for doing that, you have to study each component of the error. In fact, even we have lower bounds from at least from one of these components. So there's a very detailed study in the paper, but the essential point is the following, that for these two sources, remember that for this projection and this lifting, these were essentially affine operators. So we could essentially use the spectrum of the covariance operator for your underlying measure and for the push forward measure, as is done in statistics. And this will give you some decay, some quantitative estimates. However, the sort of the ointment, the fly in the ointment essentially is what happens to the finite dimensional projection. So there's a precise way in which you define this finite dimensional projection. This is a neural network, or it's approximated by a neural network. If it has sufficient regularity, then you get a size bound like this. Just like before, it depends on the regularity, more regular, easier to learn. However, now it depends on the number of sensor points, because there is no infinite dimensional problem. I'm approximating this infinite dimensional input by finite dimensional inputs. So I have the number of sensor points here. And of course, to get a low error, I need to get this guy to infinity, right? So because otherwise it would be a finite dimensional problem. So number of inputs, a number of sensor points goes to infinity as they're to 0. So this guy is 1 over epsilon, which will go to infinity, but the exponent will also go to infinity. So you are hit with a double curse of dimensionality that is a super expo, which is not surprising because you are trying to solve an infinite dimensional problem. So in a way, this is good news, but no good news. In general, you cannot expect that this is going to approximate arbitrary operators efficiently. In principle, yes, but efficiently is different. So bulk of the paper was to show that we can break the curse of dimensionality, but not for general operators. I mean, this would be, I think, a miracle. What it can do is that as long as your operators stem from PDEs, they have some special structural properties, then indeed you can prove that it breaks the curse of dimensionality. And we have considered a variety of PDEs in the paper. That's why it's a very long paper. But for instance, we have elliptic PDEs, conservation laws, Allen-Kahn, sort of nonlinear parabolic PDEs, Navier-Stokes. The long story short is that instead of this infinite dependence or exponential dependence on dimension, you just have a polynomial dependence. D here is the physical dimension, not the parametric dimension, because the parametric dimension is still the number of sensor points. So we were able to prove that, yes, indeed, it can efficiently approximate in principle, of course, because there still has to be, there are generalization and optimization errors. And numerically, this works. There are many more. Now I am somehow stuck. Give me 1 second. Numerically, this works very well. Let me give you one example, which is useful to convey the generality of this. I'm just taking a very simple operator here. This comes from a pendulum, a nonlinear pendulum. So this is OD, this is a toy model. So input is the forcing, which is a Gaussian random field because it's an infinite dimensional measure. So it's a law of a Gaussian random field. Output is sort of the time variation of the system. And of course, you do very well. The error is less than 1% with 100 samples or something. So it's not a big deal. But here's the promise of this, because if I would have done it parametrically, what I would have done is I would have taken a Gaussian field, done a lot of expansion, taken the first 10 or 20 parameters because it decays very quickly, and then learned the parameter to output map. Not do it. And then, of course, if you ask me to evaluate it on a Chebyshev polynomial of degree 5 or degree 10, I'm lost because my parameterization was for a Gaussian random field. But now, since my neural network anyway can take in any function, I can test it on a completely different test set on a completely different measure. And this is what is called out of distribution evaluation. So for instance, if you take Chebyshev polynomials of degree 10, this is an example. They don't look like Gaussian random fields. I can still evaluate. I don't have a theorem for it. I can still evaluate, and the error is still 3%. So this out of distribution evaluation and generalization is a big advantage of these kind of networks. We have similar results for even Burger's equation. So even with shocks and so on, it does a good job, but don't want to spend too much time on it. Okay, so this worked. So with moderate data, you can do supervised learning. You can also do operator learning. Again, moderate data is the key word. And all the time we had a PDE solver or a ODE solver where for a single sample, we had a reasonable computational cost. So for 100 samples, we could in principle do this, right? But there are many, many situations in scientific computing where even this is not available. For instance, imagine that you have a complex three-dimensional geometry or a multi-scale, multi-physics system, or for the purposes of this talk, a PDE in high space dimensions. For instance, mediative transfer equations, Schrodinger equations, and so on. Even a single solve might be very expensive. And to generate 100 samples might become prohibitively expensive. Right? So it wouldn't be feasible. So here we might have to work with no samples at all, or maybe with 10 samples, which is essentially saying no samples at all. So we can't use the supervised learning, where you give a lot of data and then you learn from data. You have to use what is called unsupervised learning. Again, there are different approaches, but in the last 1/3 of my talk, let me focus on one particular one, which is getting a lot of prominence these days. These are called physics-informed neural networks. Many people disagree with the nomenclature, but I didn't name them, so I just fixed the nomenclature that others have done. These are already available in the mid-90s. They were not called physics-informed neural networks, but they were there. They were named as such by Karniadakis again, and they have been extensively developed. I think today this paper is already cited. Their original paper in 2017 is cited 1,800 times, or some insane number. But what is unclear is why this works. In 10 minutes or 15 minutes, I'll try to explain to you why this physics-informed neural network works in many cases and where they don't work, because that's also important to learn. Let me start with a very simple example, which all of us can follow. I'm just learning the one-dimensional heat equation with 0 boundary conditions and with some initial. You give me the initial conditions. So this is your space-time domain. Space is out here, time is out here. So when I teach my students in numerical analysis 101, I say, okay, put a grid here, regular grid, then put a finite difference scheme, a Crank-Nicholson or whatever, implicit, explicit, or a finite element method. Now I will find a solution not using these methods, which will be different from these methods. So what I'm going to do is the following. First, in the spatial and temporal boundaries, as well as in the interior of the domain, I'll take a bunch of point cloud. I can always generate this kind of a point cloud. I take a bunch of random points, no correlations with each other. This is the first ingredient. The second ingredient is I need deep neural networks because I'm going to approximate my solution of my heat equation with deep neural networks, which means that these guys are functions of space and time, and they're parameterized by some parameter theta, this large dimensional parameter. So of course, then for arbitrary theta, I'm not going to even hit the initial boundary conditions, right? So my first step is at these random points in the initial line and on the boundary, minimize the mismatch with my known data, with my initial and boundary data. So this is a component of the loss function, which is well and good, right? So I want to minimize, I want to say that they fit the initial boundary data. But what about the interior of the domain? I have no data here. I'm not providing any data, but I know that it solves the heat equation. And I know that I have a neural network with a smooth enough activation function So the big advantage of neural networks is because they have these compositions. You can just use chain rule to do back propagation, and you can exactly evaluate, exactly means up to machine precision, evaluate the derivatives at any of these points. So if I fix a point here, I evaluate my time derivative, can do that because it's one of the inputs to the neural network. And I evaluate my second derivative in space, and I can evaluate a point-wise residual. So this is a residual method. I can evaluate a point-wise residual, and I'll say that I'm going to minimize the point-wise residual. Okay, so this is the roughly, I fit the initial boundary data as well as I can, and then I minimize just the point-wise residual because I know the PDE. That's why the name physics comes in here. You can argue with the nomenclature. And the advantage of this method is it's extremely easy, right? Because it, in fact, if you want to talk in terms of code, here is the whole code. Means I don't want to go into details here, but it's essentially just computing derivatives and putting them together. But you can now imagine that I can scale this up. Nothing stops me from going to 100 dimensions, right? Because I'm anyway taking random points. I can choose random points in 100 dimensions. I don't need a grid. And also, I can go to whatever PDE. Who tells me that I have to stick with the heat equation? I could do it. Wave equation, Navier-Stokes, whatever, Boltzmann equation, radiative transfer. So the algorithm is so simple. That's why there are so many citations to that paper, because many people can easily use it. But the issue is, can this work, right? We are just trying to fit the initial data. We're just trying to minimize the point-wise residual, and we say that it is going to control the error. Is that possible? So this is what I'll spend 5 minutes on. So now remember that this is my neural network or class of neural networks. This is a solution of my abstract PDE. I want to minimize the error in some LP norm. But all that I have access to is the residual point-wise. So this is a differential operator. So I have access to this residual point-wise. So I can evaluate it in some LP norm. And in fact, it's even worse. I have only access to this up to a quadrature because this is a population risk. I don't have that. I only have it to a quadrature. Could be Monte Carlo, could be something else. So by minimizing this, can I minimize the error? So this is the question, right? So it can be encapsulated into 3 simple questions. The first one is, does such an object even exist? What is the meaning of it? Just like I did for neural networks, right? Is there a neural network which is close to the PDE somehow, and at the same time whose point-wise residual in LP is small? If such an object doesn't even exist, what's the point of me trying to minimize this? So this is a basic existence question. Is there such an object? But in practice, we don't know the solution of the PDE, right? So we have to retrieve it from the residual. But the second question is, does having a small residual imply that I have a small total error? In fact, I paraphrase the question. Does having a small training loss imply I have a small residual, which in turn implies that I have a small total error? These are questions, right? Can we answer these questions? And the beginning of the answers was done in a paper that I wrote last year, but it's only recently published or about to be published. Took forever in the refereeing process. So the idea is actually very simple. So, and I'll focus on the key ingredients. My first key ingredient will be regularity, because without that, this program doesn't work. So let's imagine that I have a smooth U, sufficiently regular so that I can evaluate point-wise residuals. It satisfies the equation point-wise, okay? Then my residual error, or the residual at the neural network, is given by this expression. I can substitute this. This is a differential operator acting on the neural network, differential operator acting on the solution. Both the objects are very regular. So ultimately, with some luck, I can estimate them in terms of the Sobolev norm. So if I can approximate my neural network, my exact solution of the PDE, with a neural network in high enough Sobolev norms, which correspond to the order of the differential operator, then at least sufficient condition that I will have such an object. There will be a neural network for which the norm is going to be small. So we have to rewrite some approximation results in high enough Sobolev norms. But this is just an existence result, right? What we need is the other way around. For a small residual, do I automatically conclude that there is a small error? Yes, a sufficient condition for that is, I call it coercivity, but maybe some other people will call it stability. The bottom line is my differential operator gives me a right-hand side. So if I change my right-hand side, my inputs proportionately, my solution should change proportionately, conditional, of course, to the PDE. Okay, so this is like a stability or a coercivity statement. If I have this, and I'm going to show it in different PDEs, then what happens is that my error is given by this, by coercivity. I can dominate it by the inputs here. And since d of u equal to f, this is precisely my residual. So a small residual, and if this quantity is bounded, I have some control on it, implies that my total error is going to be small. And final piece is that the quadrature error is going to be small. So what I have done through this is that I've given a possible route to controlling the error. So we make this small, and we have some control on the quadrature error, which means that the total residual is small. Because the total residual is small and the PDE is coercive, you will have that the total solution, total error with respect to the solution is small. But this is just a program. It's like a lax equivalence theorem, but it means that you have to check it in every single case or every single class of PDEs. Quickly, this can be checked for many, many PDEs. So the simplest examples are, of course, linear parabolic PDEs, what are called Kolmogorov PDEs. You have drift, you have diffusion. So heat equation is an example, Black-Scholes equations are an example, and so on. So here we were able to prove this rather rigorously with very precise estimates on the constants. First of all, we showed that the size of the pin is only algebraic or polynomial with small polynomials in the size of the network. So there is no cursornality. We had to use something called the Dinkins formula, Feynman-Cox type formula. And then by using the stability, we were able to answer these questions that I just asked. And you see this in practice. So we have a computable upper bound, which seems to track the solution rather well. And more importantly, we also get the right scaling. So my training error, the total error scales like a square root of the training error. As you can see, there's 6 orders of magnitude in the training error, 3 orders in the realization or total error. So you can do this scaling. And it works in practice. We have been able to solve a variety of high-dimensional PDEs without any data, only initial and boundary conditions. No knowledge. The algorithm doesn't require any knowledge of the Feynman-Cox formula or whatever. So for instance, for a Black-Scholes PDE in 100 dimensions, it takes you 1.8%, 2% error. It takes about 30 minutes on my laptop. So these are really fast computations, even in 100 dimensions without any data. You can do this, and this is, I think, I'm even prouder of this because this is a PDE that I have always struggled with to numerically simulate. Radiative transfer equations, you don't have 100 dimensions here. In the worst case, you have 7 dimensions, but the PDE is, it has non-local effects, it has transport, it has diffusion, so it's a mixed type, multiphysics PDE, and you can do but more importantly, you can do computation. In this case, for instance, it took us 57 minutes or 66 minutes, but 66 minutes for a 6-dimensional problem. So there's a 6-dimensional, fairly realistic example test case where we have some analytical solution, and took us 66 minutes on the laptop to do this, and with 2% error. So this is sort of physically realistic example. You can do Navier-Stokes. I don't want to spend too much of time on this. I'm running out of time. You can do Navier-Stokes. Again, the key point here is regularity, because I assume the regularity. So, and some control on the vorticity, just like for classical numerical methods. If the vorticity blows up like it would in 3D, then you're out of business. Just like a finite element method is out of business. So it's no worse than that. You can do dispersive PDEs, KDV, Benjamin Ono, and so on, because these also have the regularity and they have the coercivity. So you can do solitons to very, very high accuracy. Even this non-local soliton, it's less than 1%, takes a minute, I guess. And you can see that it resolved the interaction of these solitons quite well. Do full nonlinear PDEs. Many people in Paris work on this. Monge-Ampere, Hamilton-Jacobi-Bellman equations. Of course, now the theory is W1 infinity theory, right? You can't use L2 loss functions. You have to use L infinity loss functions. So you can do like 20-dimensional Ampere equations, which is quite good. And here's another important point. Remember that this is a mesh-free method. I'm just using random points or Sobol points all the time. So for instance, we are trying to solve the Monge-Ampere equations on a sphere. So I take a bunch of points in the boundary of the sphere and a point cloud in the interior. You get 2% error, but you solve the problem. No need to generate any kind of grid here. So when it works, it really works. But maybe I should also warn you that it can't be every single situation. The analysis tells you when it doesn't work. Remember, I kept on talking about regularity all the time, right? So here is an example where it doesn't work. And this is the Burgers equation, the viscous Burgers equation. See, I quote the implicit limit in a bit. You do the analysis that I just suggested, and then you see that the constants here depend on the L infinity norm of the gradient. But as the viscosity goes to 0, the L infinity norm of the gradient blows up. We have the formation of shocks. So it cannot work, right? Because the theory says, okay, these are overestimates, but the theory says that it cannot work, and it does not work. So for viscosity, which is finite but small, it works well. But as the viscosity goes to zero, things blow up. So regularity is the key here. On the other hand, if you look at rarefactions, these are also nonlinear waves, but now the gradient is bounded in L infinity. So as the theory suggests, it works quite well. So there are limit cases. So in general, when the pointwise residual can't control the error, these methods are not going to work. So in that case, you can't work with the pointwise residual being in LP. You have to work it in a negative Sobolev space. This means that you have to use some weak formulation. And there are many different weak formulations out there. They're coming one by the day. But the one that I like is actually a fully weak formulation. Everything is on the test function. My neural network is, my solution is approximated by neural networks. My test function is approximated by neural networks. And then what I do is min-max. So I maximize over the test function, I minimize over the solution, and then you essentially play the game, which is similar to what is done for GANs. And by doing this, it's still very preliminary work. The theory is still not, and you have to also put in entropy conditions because we're solving hyperbolic equations. But remember, this didn't work. It gave me 20% error, but now I'm getting it down to 2% for these equations. Early days yet. I have 3 minutes, I think. So I'll try to, can I take 2 extra minutes, Albert?
Go ahead.
Okay. So again, the whole theory, why do I even care about pins, right? So remember that if I had moderate data, somehow I could have used my classical sort of supervised learning. The point here in all the examples that I showed you, it didn't require any label data, which means I don't require any data about the solution. Boundary conditions, initial data, of course, someone has to give them, right? Empirically, if some small amounts of data is available, then it definitely helps the empirical performance. But what about those problems where the data itself is a part of it? For instance, I have some data, some measurements, but I don't have knowledge of the boundary conditions or the initial data. Now, these are inverse problems, right? Where some examples where data is a part of such problems, and pins are really powerful at these kind of problems. Let me talk about one of them, which is this data assimilation problem or unique continuation in the steady case. So you have the PDE satisfied in the entire domain, you know that, but for some reason you can't measure the boundary conditions. What you have measurements on the interior, some point measurements on the interior. Now you can do a pin in this particular case. You know that the PDE is set of holds all over the domain. So you take that into the residual, and instead of the initial and boundary data, or boundary data in this case, you just add this extra data points. And then you minimize them. It's the same. There's no change in the code. There's no change in the complexity. Algorithmically, you get a single shot solution for an inverse problem. But again, can we do the math here? In some cases, yes. So one example, there are many examples in this paper, but one example is for Stokes. Navier-Stokes, we still haven't succeeded in doing it yet. But for Stokes, yes. So in this circular domain, I have measurements of velocity, no measurements of the pressure, and I want to find the solution everywhere. Okay, both the velocity and the pressure. So in this case, the coercivity, the theory is exactly as what I suggested before. The coercivity is provided by the Kalaman estimates. Many people in Paris know them, have proved them. This one in particular is from Gunther Ullmann for our setting. And you can prove that indeed, if my training errors are small, both with respect to the PDE and with respect to the data, then, and you see that in practice. So for Navier-Stokes, but we have not been able to prove that. So this is the ground truth, and these are my pin reconstructions, and they're very close to each other with very few points, even for the pressure. Remember that I had no measurements for the pressure. I could still get like 3%, 3.5% error. Single shot. So this entire calculation takes 5 minutes or 3 minutes. I don't remember how much now, but at one go, you solve the PDE and the inverse problem. And this is also done, okay, I don't have time, but this is also done for seismic imaging in this particular case. You want to reconstruct this permeability field, you have the Helmholtz equation, and this is, it's not unique, of course, because it's the inverse problem, but in this case, you get something reasonable. So I think with that, I try to cover a lot of ground, but it's important also for me to summarize, and this is important. So deep learning for PDEs, and I just presented a very particular viewpoint. There are many, many other people, and they have different viewpoints, which I respect, of course, but in this particular case, for me, the important thing was the role of data. So we can't expect big data. This is not possible, I think, in general, in practice. So we have to live with moderate data. Supervised learning works fine. You have to do all these tricks. You have to choose the training sets appropriately. And then I showed you several examples and some theory why it works. Now, if you have non-parametric regime, you have no parameters, then you have to use operator learning. Even there, operator learning, of course, is a superset of the supervised learning with moderate data. So that's very powerful. But if you have no data or very small amounts of data, then pins, especially for problems with regularity and coercivity, they're very efficient and very useful, particularly for inverse problems, because in single shot, you can solve the inverse problems. And this was sort of the main point. Of course, there are many caveats here, right? And some of them I tried to flag during the talk, but let me flag some of them right here. So this was sort of the abstract error estimate, the best error estimate that anyone can prove, right? So the total error depends on the training error, depends on the details of the quadrature points and the details of the PDE that you have. So roughly, this is the meta estimate that you can prove. I spoke a lot about the behavior with respect to the number of training samples, something about the PDE, something about the neural network, but I didn't speak at all about the training error. And this is for a reason, because I certainly don't know how to control a priori the training error, right? And I don't think anyone else does either, at least sufficiently strongly. And why is that? Remember that in some of the last examples, I had even neural networks which had 100,000 parameters. So it's, and I had to optimize over a non-convex problem in very, very high dimensions. Not only is that a horrible thing to do, but these loss surfaces, they really look bad. Not me, but some people in computer science have tried to visualize, they've tried to project it down to 2 dimensions, 3 dimensions in this particular case. So this is your loss surface, 2-dimensional, and you can see how nasty it is. There is a global minimum, but you can see all this jaggedness and all these hills and valleys here. So how are we going to prove theorems about this? Right? I mean, this is a tough challenge. Of course, there are some ideas out there. So this means that training is time consuming, not because the training itself, but because we have to tune hyperparameters. You can hit local minima, there is saturation. I could never get the error down to 10 to the power less than 0.01%. It's not possible. It's not like a traditional numerical method where you can get 8 digits, but you always get like 1% error. So this is sort of a golden, but it's still very empirical at this level, right? Another problem is that you don't have sharp estimates. Means you have estimates, but you don't have sharp estimates. In fact, for pins, I had fairly sharp estimates. Surprised how sharp they were. For instance, for Navier-Stokes, I had something like 1 order of magnitude. This is a blessing. It doesn't really, we are lucky. It doesn't really happen. Sometimes these estimates are way off, So this is because we're using statistical learning theory. And statistical theory at the moment does not have the tools to estimate sharply some of these things, even in classical machine learning. And the last point is that not just me, but everyone else in the field, our choices of network architectures are very conservative. We're taking fully connected neural networks, recurrent neural networks, or let's say convolutional neural networks, something residual, ResNets, and so on. Very conservative choices. On the other hand, I know from my work on traditional machine learning that by choosing lecture based on your problem, there could be major gains. So there is a scope for sort of novelty. Should the neural networks that are useful for imaging be the same for PDEs? Perhaps we should think in terms of investing in novel architectures. But they're vague ideas, but nothing concrete has yet come out, not just from my research, but from other researchers also. So there are many caveats, many issues, so many different problems to solve, but there is some potential here. And that's all that I wanted to convey. Thank you very much for your attention. And my apologies for taking 3 minutes extra.
Thank you very much. Okay, so are there questions? So we can have questions from people in the room and from the participant. The participant should simply raise their hand. Let's see. First, are there questions in the room?
Yes, I can ask the question to you. But my question is, to be more precise, what do you call big data? What you call big data, it means the data which was not in the data set, essentially at the end of the day. Is it that what you mean by big data?
No, okay, I have a very specific, this is a difficult concept, right? Okay, in fact, I can explain it in terms of the last estimate here, right? So for me, data is simply the number of training samples that I need in my method, right? So this is for me the data, the number of training samples that I need, right? And especially in these parametric problems or also in the operator learning, this is the number of sort of points that you get in parameter space. And remember that each of this is either generated by, think about a shape of an airfoil or a shape of a whole aircraft or something like that. Each of it is generated by numerical simulation, or even more expensively by an experiment, right? So for me, data is simply training data that I feed into my algorithm. And big data is if I have, let's say, 100,000 training samples, then it's n to the power minus alpha. So if it's 100,000, then if alpha is a half, then I get a low error. If not, if I have only 100, then 100 to the square root of 100 is not a big number. It's 1/10, so I get 10% error. So this is in the sense what I talk about big data. So data is just the training data that I provide to the system.
It's more the cardinality of the data set. It's the number.
Cardinality of the training set. Yeah, absolutely.
And my question is, for pins, when you have to something about the boundary conditions or what, to sample the boundary condition of the numerical value of the boundary condition. So if then when we use the pin to predict something with the data on the boundary or initial data which is outside of the ball of all everything that we have sampled, what will be the quality of the result? This is my question about.
Okay, I think I got your question. Now let me try to explain it to the audience a little bit in my language. So what Bruno is asking is exactly about, so this is, let me explain it in the following. It's not just about pins, Bruno, it's in general. Your question, I think, is very, very general. So I will answer it in some generality because I have an example about this, right? So here is an example. So this is a simple problem, but nevertheless, it's very instructive. Okay. So what you do here is that the training data set here has been Gaussian random fields of a certain correlation length. Okay. So all the training samples have been sampled out of Gaussian random fields. And now the question that Bruno is asking is, okay, the Gaussian random fields. So make a different function from ground to Gaussian random fields. So you are still in distribution. You're taking the same underlying measure. And then, of course, your mean test error is like 0.7%. But what is very instructive is to ask what happens if I test outside this set, right? So in other words, if I can, instead of testing for Gaussian random fields, if I can test for Chebyshev polynomials of degree 10. Now it has never seen a Chebyshev polynomial of degree 10. It has only seen Gaussian random fields. Can it learn this? So the theorems that I have is no, because I needed an underlying measure, a very, very clear underlying measure. And using this underlying measure, I was inferring what I was inferring, right? On the other hand, at least operator learning gives me a route, gives me a way in which I can evaluate this. And this is what is done here, right? And the best theorem that I can prove is that if my measure is perturbed, if my measure is different, then of course the total error scales as the difference of the measure in the Wasserstein metric. I can prove that. But of course, how different is the Gaussian random field in the Wasserstein metric to Chebyshev polynomials of degree 10? Nevertheless, it's in principle possible. In the parametric regime, it is not possible. Even with pins, means it is not possible. Of course, you can combine pins with operator learning, right? So to do this, you have to do other things. You have to do what is called transfer learning. That is, maybe it has seen Gaussian random fields. Now it has not seen Chebyshev polynomials, but maybe these are not too far. So maybe by just massaging or training a few weights, I can recover the solution of corresponding to Chebyshev polynomials. That's one possibility. Another possibility is meta-learning, which is common in computer science. There is learning to learn, where instead of having one measure, I have somehow parameterized over many different measures. So I train on some of them and I test on some of the others. And then there's also causal learning and so on. But this plain vanilla approach, you cannot expect that if you're completely sampling outside your distribution, then you will have, it's the same with the pins, right? Pins, then you have to solve it again. So let's say here, I'm not having any parameterization whatsoever. You give me the initial data, it's like a new numerical method, right? So give me sine wave, I solve for it. If you give me a Gaussian random field, I again have to retrain the pin and solve. If I can't parameterize it in one go, then this is the price that one has to pay. It's a long answer, but I hope that at least I pointed out the issue to you, Bruno.
Other questions in the room or in the participant?
There is a question by someone.
Frédéric, please.
Yeah, okay, yes, thank you. And thank you for your talk. It was very interesting. So my question is about, let's say, preconditioning. So could it be possible to use machine learning techniques when you want to solve the exact equation but you would say you would use the surrogate model as a preconditioner to speed up the solution of the high fidelity model.
Brilliant idea. Yes, that's a very, very nice idea. And indeed, I don't know if someone is doing it. I know you are the expert in preconditioners, so it's this is
That's why I asked. Yes.
This is a very good idea. I didn't think of it, but indeed, why not? Means this is you have a surrogate which is very cheap, right? But indeed it is. And in fact, I will even go further, because what you can do is, we have done a little bit of multi-fidelity modeling and training and so on, and some other people have also done this. So what you can do is you can combine them. You can run, even during training, you can generate some very high fidelity simulations. A few of them, you have several low fidelity simulations, and you train on that set. So indeed, you can use this as a preconditioner, and then or some elements of it as a preconditioner, and then speed up the overall problem. But yeah, one has to look into the details, of course. But I think it's a very, very good idea. I have not done it, so I can say no more.
There is a question written by one of the participants asking about the use of pins in inverse problem. For example, assimilation. Do you suppose the size system dynamic fully known?
Yeah, I see the question.
Can you expect the neural architecture to learn the missing physics?
Not the missing physics. I mean, that would be asking too much. But what you can do is the following. Okay, maybe I used to have always, okay, let's look at the radiative transfer equations. I don't have the answers. Okay, let's look at the radiative transfer equations. So, of course, many people know the physics of the radiative transfer equations. They know the form of the equations. What is usually missing is you don't know K is, you don't know what sigma is, you don't know what the scattering kernel is, and so on. You don't know these things, right? So now what you can do, and what we have also done to some extent, is you just replace. So U is a neural network, or U is approximated by a neural network. These guys are approximated by neural networks, and you have measurements, and then you infer these values from measurements. This is possible. But it giving the form of the equations means you only have some coefficients in the equations that are missing, right? Now, if you want to learn the entire equation directly, so there are some methods, people in Nathan Kutz and so on, they have some methods in this direction. I don't think it's a good idea personally, because in many cases we know the physics. We may not know the coefficients, but we know sort of the basic physical laws. And if you don't even know the basic physical laws, then we perhaps shouldn't use PDEs to model those things, right? We can use operator learning. These are still operators. These are still mapping between infinite dimensional spaces and infinite dimensional spaces. If you have a lot of data, you will infer the operator and then just evaluate the operators. You don't need to know the physics. These are for problems where the physics is known, maybe some coefficients are not known, and where it's expensive otherwise. So this morning, I'm working with some people in a big lab here at ETH, where they're doing 3D printing. And the equations are known. This is some nonlinear heat equation. 3D printing, your laser moves through and it's just melting things, right? But it just takes forever to simulate it using a finite element method. So on the other hand, this reduces the computational cost considerably. That's the way you should think of it.
Okay, other questions? Maybe I had a question. I would like somehow to delineate in all these range of problem. I mean, for what problem the use of deep network is really critical? Because, for example, in PIN, okay, you insisted on the need for regularity, for smoothness. And when you have, when you are, because you are measuring things with residual, you need to be able to say something about this residual when you measure it in a Lebesgue norm. And then, if you have smoothness, essentially, you could train something else than neural network. You could train spline functions or much more classical, actually even linear things for which you would have less problem with the optimization.
I agree that this is a very, very good question, right? So if you have regular problems, if you have enough regularity, can linear regression beat pins? The answer is no. There is no theorem. There's no theorem about it, but in empirically, means it simply is not able to beat pins. And but why should you stick to linear regression? You can try to, for instance, do splines, as you said, or radial basis functions. I'll tell you, computationally, neural networks are still advantageous because you can back propagate easily. So there is a computational reason that you can do automatic differentiation, you can backpropagate easily. And but there is, in principle, you could have used radial basis functions, right? Means I don't know how well radial basis functions are going to capture 100-dimensional function. So regularity is a very subtle thing, because you can do problems which are not regular. For instance, here you have a discontinuity and I'm still able to approximate it to 0.3%. The regularity is measured in the sense that the pointwise residual does not control the solution. Because I can always approximate, this case, I can approximate it by something smooth, and then that smooth object's residual is well behaved, and that object is well approximated, and I can pass to the limit. For conservation laws, I cannot do that, right? So it's a bit more subtle, but I see the point perfectly. Still, I would argue that for computational reasons, you would prefer to use something like neural networks, where you can backpropagate and so on and so forth very efficiently. You can do it with radial basis functions and so on. Linear interpolation, linear regression, you don't have universality anymore, no? Means it's sort of, you can't approximate nonlinear functions by linear functions. Means somewhere it should break down, right? Maybe from the data, yes, if you have a lot of data, but now in this unsupervised regime, I don't know if it makes sense, right? So you're saying that my approximation will just be a line.
Well, okay. No, I was just saying that you have chosen a machine learning strategy. There are many other tools.
Yes.
Machine learning, that there is random forest, there is
you can do random forest. By the way, these things are all we have also done some work on random forests and Gaussian processes. Why do I insist on neural networks? A, because as I said, computationally there are advantages to it. That B, so there's computational advantages, there is universality and so on. So there are some theoretical advantages also, but are there problems where neural networks absolutely beat everything else? Means even theoretically, I think Ron DeVore and so on, they're looking at these, this better than I do, right? They look at this sort of fractal type objects. I just doesn't mind, and their neural networks are beating other families of universal approximators, because I could have also used Fourier basis, I could have used wavelets and so on and so forth. But and another thing is neural networks can approximate all these libraries, right? So this is what Helmut, Boltzkai, Philippe, and so on, they have proved that all these libraries can be approximated by neural networks. So I do agree with you that the theory is very, very incomplete, because clearly something more is happening, which makes it work much better than what we are able to show, right?
Okay, thank you.
There was a question on the chat that someone is asking, Simon. Architecture is thought for strong solutions, and the problem, for instance, for solving Burger's equation. Yeah, very good question. Burger's equation, as I showed you, you don't solve it, because there is a theoretical reason why you don't solve it. But there are weak formulations, and one weak formulation is this min-max, this sort of adversarial training. I call it as weak pins, weak pins, and there you are able to rid of. But it's still, now the training is more complicated, because you have min-max, it's computing saddle points, and this is harder. But this is, there is an enormous branch of computer science of machine learning on adversarial networks, where lots of different training algorithms have been proposed and so on and so forth. So this is still in the beginning, but I believe that there will be natural weak formulations. If there is regularity, I would not use them, but if there is no regularity, one has to develop in this spirit. But there are other people, for instance, they say that instead of the test functions, I just look at a span basis functions, Chebyshev polynomials or Legendre polynomials. They call it as variational pins. They also get very, very good results, maybe not for hyperbolic PDEs, but for elliptic and parabolic PDEs. But the advantage of this is that it's a complete neural network method. There's no grades, nothing. So there are some advantages.
Okay, thank you very much.